Okay, so welcome everybody to our second and last day of this Interacting Stochastic Systems session. So it's a pleasure to present our first speaker today, Alessandra Cipriani, who's going to talk to us about random interfaces beyond ZD. So all yours, Alessandra.
Thanks, Daniel, for the introduction. Welcome, everyone. I would like first to thank the organizers of this session for, first of all, for inviting me, and also for their efforts and help for registering for the conference, which was very much appreciated. So I said, so today what I would like to talk about is this joint and actually ongoing work that I'm going to present on random interfaces beyond CD. And that's a joint work with these three people, Bill Tudan from Bangalore, Rajat Hazra from Leiden, and Runa Krai, who's now in Eindhoven. So what we would like to do here is to talk about or discuss properties of random interfaces, but not in, I would say, traditional or standard setting of Euclidean geometry, so on the square lattice, but we would like to study random interfaces on more general graphs. So to, of course, discuss the results I want to present you today, I first need to describe you what a random interface is. So, and I will start with the definition of interface in general. So interfaces can be defined on any graph. So you give me a graph with its vertices and edges, and I can, in general, define an interface on the graph simply as the graph of a vertex function. So what happens is that for any graph, say in this case, I have this sketch on Z1, in fact. So for every vertex of the graph X, I'm going to attach to it a height, which I'm going to call phi of X. And phi of X will represent the height of the interface at side X. Then what I can do is I can interpolate this interface, say with a linear interpolation, a very simple one, so as to create a continuous surface, if you want. So these interfaces are used, come from biophysics and physics literature to model separating surfaces between different media. And you can imagine that in nature, interfaces are not deterministic in general. There is some randomness to them. So what I would like to do is I would like to put the probability measure on possible height configurations. So how am I going to do this? Well, I'm going to use, if you want, the classical Gibbs formalism. So I'm going to define a random interface now via probability measure. And this probability measure requires two ingredients. One of them is a Hamiltonian, or if you want, an energy function that is going to give me the energy of a certain height configuration. And the second ingredient I'm going to need is this subset of the vertex set, lambda, which is a finite subset and connected in the graph sense, so finite and graph connected subset of the vertices. So with these two ingredients, I'm going to define this probability measure. So this probability measure is something that probably some of you already recognize. So what I'm going to say is that the probability of my height configuration is proportional to the product Lebesgue measure for heights whose vertices are inside lambda. And this product Lebesgue measure is weighted by the exponential of minus the energy. And then what happens outside of lambda is not really interesting for us, because what I'm going to set, I'm going to set the so-called zero boundary conditions outside of lambda, in the sense that my interface has height 0 whenever a side is not in lambda. So essentially all the randomness happens for heights inside lambda. Now, to make this idea or this probability measure concrete, I want to show you a simulation of a very well-known interface, which is the discrete Gaussian free field. So here as lambda, I used a two-dimensional discrete box, Z2. Everything outside is set to 0, and then I've sampled certain heights for every lattice point inside this lambda. How did I sample these heights? Well, I want to define the probability measure of the discrete Gaussian free field on boxes of ZD. Say now, in general, the side length, I'm going to call it big N. So I'm using this notation twiddle to denote graph nearest neighbors in ZD. And the ingredient I need to give you, once I've given you the lambda box, is the Hamiltonian, the energy of the configuration. And the energy of the configuration for the discrete Gaussian free field has this form. So it's essentially the inner product between the height field and its Laplacian. So what the graph Laplacian is, so if you take the graph Laplacian delta of a height configuration evaluated at a point x of the lattice, what you're getting back is the mean height of phi of the configuration around that point. So essentially, the graph Laplacian is doing what the continuum Laplacian does in RD. So averages out a function around the point, or gives me back the average around the point. And essentially, the Hamiltonian of the DGFF is already telling you what the DGFF does as a configuration. It tries to be harmonic. So the fact is that you can express the probability measure of the DGFF in another alternative way. And it is to say that essentially what you're sampling is a multivariate Gaussian on lambda, indexed over lambda. And this multivariate Gaussian has mean 0, the 0 vector, due to the 0 boundary conditions I set. And the covariance matrix, which I'm going to call G lambda, solves a discrete boundary value problem. So for every x in lambda, the G lambda xy essentially inverts delta, or actually I should say minus delta inside the lambda, and is 0 for every point which is not in lambda. So all in all, this tells you that the covariance matrix of the GFF is nothing but the inverse of the minus delta lambda matrix, where delta lambda is a matrix that restricts the graph Laplacian to entries, that belong to lambda. So it's the restriction of delta matrix of the operator inside of lambda. This representation is very useful. Why? Because it connects you, the Gaussian free field, to the simple random walk. So let's say that you want to evaluate the covariance between 2 points, x and y, under the DGFF measure. Well, this covariance can be obtained in the following way. You take a simple random walk on the square lattice, you make it start at x, and you count on average how many times this random walk returns to y before exiting lambda, your finite domain, say the box. And this expression, this average, this local time of the simple random walk gives you a lot of information about the Gaussian free field. For instance, a one-line proof tells you that you can define a discrete Gaussian free field on the entire square lattice, so not just on a finite box, when you are in dimensions higher than 3. Because using the transients of the simple random walk, you can see that essentially you can remove the condition of being killed upon exiting lambda. The random walk is transient, so on average it will return finitely many times to the point y. So essentially this Gaussian free field, this multivariate Gaussian, has a finite finite covariances or finite variance everywhere on ZD whenever D is larger than 3, so you have an infinite volume measure. So this is very, very little about the Gaussian free field. What I'm interested in now is to say, okay, can I study other types of interfaces? And the other interface I want to study is this one. It's called the discrete membrane or Laplacian model. And why it's called Laplacian? Well, you can see that if you look here at what I wrote under the simulation. So what am I going to do here on a finite box of ZD? I'm going to do the same as I did for DGFF, so sampling a centered multivariate Gaussian. But now the covariance matrix I want to impose is the inverse of what I'm going to call delta lambda squared. So now let me zoom in on this delta lambda squared. What is it exactly? So in general, as you define the graph Laplacian, you can define the graph B Laplacian. The graph B Laplacian is just the iteration of the Laplacian on itself. So this is a matrix indexed over ZD times ZD. And again, it's easy to say, okay, I can just restrict my entries to being inside of lambda. I can do that without any problem. So you can ask me, what's the relation between delta lambda squared and delta lambda squared altogether? And let me pose delta lambda everything squared. So what's the relation between the covariance of the membrane and the DGFF? Well, actually, you can prove that iterating delta lambda on itself twice is not the same as taking delta lambda squared. So commute the square and the restriction do not commute as operations. However, you can still prove that delta lambda squared is a nice symmetric and positive definite matrix, so you can invert it. Our measure is well defined. Our Gaussian is well posed. I can define the membrane model on a finite box. And again, the situation is very similar to that of the DGFF because you have, again, a multivariate Gaussian with this covariance matrix, which again solves a discrete boundary value problem. Essentially, what you're doing here is you're inverting the B Laplacian operator rather than the Laplacian. Okay, so you say, am I repeating everything that I've said before? So you may guess what I'm going to do next is I'm going to talk about the random walk representation. But the random walk representation for the membrane is a bit more complicated, and that's due to the fact that restriction and square do not commute as operation on the graph. So I'm going to reverse a bit my viewpoint, and I'm going to start already by talking about infinite volumes rather than finite boxes. Because in infinite volumes, what you can actually prove is that if you take the limit, the operation of squaring and restricting are commuting. Actually, you can say I'm forgetting about restrictions because I want to take a measure on the infinite lattice, so boundaries do not play a role anymore. So you can prove that you can convolve delta minus 1 with itself on an infinite lattice. And whenever the dimension is higher or equal to 5, you can actually prove that there exists a delta squared inverse. And this delta squared inverse defined on the entire lattice is nothing but the following expression, which represents the mean local time, the intersection local time of two simple random walks on ZD. So you take two independent random walks, simple random walks, one starts at X and one at Y. You count how many times they intersect on average. This is going to represent the inverse of your B Laplacian operator on the entire lattice whenever D is larger than 5. So essentially, this means that you're justified in defining a membrane model on the entire ZD. Your guess may be, in finite volumes, I want to take the same thing, so the intersection local time, But now I want to stop the two random walks as I did before. You want to stop them whenever one of them exits lambda. And you want to ask, is this the covariance matrix of the membrane? And you can prove that actually this is not the case. So this expression of intersection local times stopped at exiting lambda is close to the real covariance matrix, the true covariance matrix of the membrane model, but it's not quite the same. This approximation is a nice approximation whenever d is larger than 5, and it's actually a bulk approximation. So it's an approximation that goes badly when you're trying to approximate covariances close to the boundary of your box. So the problem that this approximation is not good on the entire box led us to try to study or try to find an approximation or an expression for the covariance matrix of the membrane. And here I want to mention that when one tries to study the membrane on ZD, one has the help, so one doesn't have the random walk representation, but what one can use are techniques from numerical analysis, essentially. So you can try to approximate the continuum boundary value problem with a discrete one. And you can use tools from numerical analysis to quantify the goodness of your approximation and thus study the membrane model. This is not something that you would do for the Gaussian free field. But the fact is that numerical analysis techniques are good, say, on lattices that approximate something, but they may fail when you try to go to other geometries. So since our goal was trying to go beyond the ZD setting, we were thinking, can we find other proofs or can we find other tools to study the membrane? So we actually rely on, I call it new representation, but in fact it's not new. It's due to van der Bij, and it was proved in 1984. So this representation requires, you are going to see that it's a bit more complicated than that of the DGFF, and requires actually not just the first hitting time of the boundary, requires successive hitting times of the boundary, or I should just say of the complement of your set. So let's say that, for instance, you have your lambda, your box, and you study the times, or you count at which times your random walk is outside of lambda or touches at the boundary of lambda. So for instance, this is to 0, this is the first time, this is the second time, and then again the random walk stays out of the box for another time. To 3, I guess this is going to be to 4. I'm sorry, my drawings are not really on scale. To 5, then the random walk stays inside lambda, exits again at to 6, and so on and so forth. And then you're going to need this MJ, which are the product of the successive hitting times of lambda complement, if you want. And what van der Bij did was to prove this representation. So essentially, let me guide you through this slide. So what he proved was that if you take the true covariance matrix of the membrane model, which I call G lambda, and you want to approximate it with the intersection local time of two simple random walks killed upon exiting the boundary of lambda, well, the error that you're getting is this expression here, which is rather long and complicated. You don't have to see it through the entire expression. I just want to mention that this expression here requires an auxiliary truncation. What do I mean by that? So you see here that there is this eta t, which appears in the sum. So eta t is a Poisson process of intensity 1 that's independent of everything else, and that you need to insert in this error term, because you can prove that there are graphs where this approximation here is actually infinite unless you put the truncation of the series at eta t. So this representation, I hope you agree with me, is more complicated with that of the DGFF, has some disadvantages. One disadvantage is that this heating excursion or heating times depend a lot on the geometry of your lambda. So you can imagine that you can have domains which are very, I don't know, thin. And once you step outside of them, once your random walk steps outside of them, it's easy to stay outside. But there can be other domains where once you step out, it's easy to come back, to return to your lambda. This representation has, however, one advantage, one big advantage, and that it's that it works for any graph. So what van der Bij proved is that this approximation via intersection local times is actually a representation that works for essentially any graph. And that's what allows us to study the membrane model, for instance, in other geometries like trees. And in the final 10 or perhaps 8 minutes that I have, I would like to present you our results. So here what we are doing is we are replacing the square lattice with the tree. I have the infinite ZD lattice, which is now replaced by an infinite M regular tree. And on the infinite regular tree, my box lambda is going to be replaced by essentially a subtree of Tm of the infinite tree, which now has n vertices. So the side of my lambda is going to be replaced by the number of vertices that the subtree has. So on this graph here, we can define a membrane model, again, with zero boundary conditions outside the subtree, and we can see what happens to it. So again, here I'm essentially repeating van der Bij's representation. So the covariance of the membrane is the intersection local time plus this long and big green arrow. And what we're able to prove is that there exists an... Yes.
Just a quick question. This M that appears in the formula, is it important, or maybe I missed if you the mj minus 1 in the...
So this mj minus 1 are the product, is the product of the, how can I say, the excursions between successive times when you are outside of lambda. So yes, they do matter in the proof. One thing you can say, and that helps us, is that, of course, if you stay for 2 time steps outside of lambda, this mj is going to be 0.
Okay.
Because tau j is equal to tau j minus 1 plus 1. So, of course, this expression is going to be 0 whenever you are for 2 consecutive time steps outside of lambda. So they matter up to a certain extent, if that
close to the boundary. Okay.
Exactly, or close to the boundary, yes. So then very briefly, so what we're able to prove. So the first thing that we're able to prove is that actually there exists an infinite volume membrane. So we can push this multivariate Gaussian to stain on the entire tree. And what we're able to prove is that in infinite volume, we can study the covariance of 2 points on the infinite tree. And the behavior actually is that of very fast decaying correlations. So correlations decay like the distance between points, time, essentially an exponential or a negative exponential in the distance. So they are very fast decaying. And just to recall you, if you want to know what happens when you are in ZD, the behavior instead is slower, or the decay is slower, it's like 4 minus t. For t larger than 5. So here we are in a situation where you decorrelate rather fast. There is an infinite volume measure. So what you hope is that you can repeat, or you are in the same regime of the membrane model in so-called higher dimensions when you have an infinite volume measure. So what we're interested in studying are, for instance, the extremes of this interface. And what we're able to prove is that if you rescale suitably the maximal height of the membrane model on your finite tree, what you're getting is convergence to a Gumbel distribution. And that hints to the fact that you are in a so-called supercritical regime, if you want, for the membrane model. So your Gaussians tend to behave like IAD Gaussians, and that compares with analogous results for supercritical interfaces compared, say, to what happens for log-correlated models, for instance, and thinking of the Gaussian free field at critical dimension 2, or the same membrane model in ZD for D equal to 4. So you are here in a more independent setting due to this fast decay of correlations. And again, the same result, we can prove it for finite volumes. So now we are not studying the measure of the membrane on the entire tree. We are studying it just in this portion lambda n. So it's a slight difference, but the principle is the same. You are getting, again, convergence to a Gumbel distribution. And I have 2 minutes, perhaps, to go very briefly through the, thanks, Daniel, to go briefly through the proof. So the existence of this infinite volume measure is something relatively easy. So on the tree, essentially what you have to show is that the intersection local times are finite. This is a computation that you can derive, for instance, by knowing the Green's function on the M regular tree. What is a bit more difficult is that you need to prove that the difference between the true covariance matrix and the intersection local time is converging, so that actually the error term is going to 0. So the key point here is that you're able to prove that the error estimate is actually going to 0, like, okay, m-1 times to the power minus the distance of the 2 points to the boundary. So if you push the boundary of your finite volume to infinity, the error term is going to 0, and this is going to help us, or enables us to say we are really getting a good approximation by using intersection local times. And for the maximum path, here I want to say that the idea that we are using is that we are again in a supercritical regimes with fast decaying correlations. So what we want to do is we want to study the exceedances of the interface over a certain threshold and apply a so-called Stein-Chen method. So we want to prove that the number of exceedances is roughly behaving like a Poisson random variable. That's a technique that comes from extreme value theory, essentially. And our procedure is that of applying the convergence of the number of exceedances to a Poisson random variable. So we need to prove that in total variation distance, but let's just say you want to approximate the exceedances with a Poisson random variable with this mean number, which is actually the mean number of exceedances, and finally prove that this Poisson lambda n variable has the right parameter. This part here, though, is not really concerning. Let's say what is a bit more involved is to use or to prove this first step. And for that step, again, we are in this supercritical regime somehow for random interfaces when we are able to use the Stein-Chen method in the version that was developed by Holst and Jansson in the 90s. So this was a brief introduction or different viewpoint on random interfaces from square lattices to other types of graphs. So we hope to be able to study different types of geometries, not just trees in the future. But for today, I think I want to stop, and I would like to thank you very much for your attention.
So let's thank Alessandra for this very nice talk. Actually, I don't, this is my mistake because we should have gone to questions first, but then we get to thank Alessandra again. So I don't know. So are there any questions? We have time for some questions. So.
Hey, Alessandra, does the representation itself work at first for other geometries, and like how regular do you need your graph to be? Okay.
So, okay, one assumption that you need is that the second moment, so maybe I should try that somewhere else. A lot of extra slides. So I think you need that the second, for every point, the second moment of τ0, which is the first time when you step out of, say, your finite volume, where you're actually considering your interface, you need it to be finite.
Mm-hmm.
That's one assumption that you need. And then I think you need some regularity assumption on the boundary, the first boundary and the second boundary, but I do not remember precisely the condition, but I think it's a very natural condition. So you have to be really, really degenerate in your graph to say, okay, this condition doesn't hold.
Mm-hmm. Okay, thank you.
Are there more questions?
Yes.
Paulo?
Yes, Alessandra. So somehow you have a thermodynamic limit, right, of finite regions to infinity, and you told us that you have this difference on the covariances, and that the covariances of this Gaussian field converge. Can you use this to make a construction of the field, like a simulation? Or how did you produce the picture that you showed us?
Okay, so the picture was cheating, in fact, because so you caught me there. So actually, what I did in the okay, I have to find it somewhere. So the simulation I did there was one that I put on the square lattice, but in fact it was for periodic boundary conditions. So essentially what I did there was convolving the or squaring, if you want, the eigenvalues of the graph Laplacian. So that was a bit cheating when I wrote it there, or when I drew it here. So what you would need to do if you had it properly would be to say, okay, you determine the eigenvalues of the B Laplacian on this lambda or wherever you need it, and then you simulate your membrane model. The other point is that the intersectional random walk approximation just works for D larger than 5, so it's not really something that you can show or that you can visualize.
Okay. Okay, thank you. Thank you.
Okay, we have time perhaps for one more quick question. If there is any. I have a very short question probably. Is the continuum limit of this well defined? Is it known? Like the square version of the GFF or something like that?
So for ZD, yes, for ZD, you have a continuum version of that, which is, again, it's like the continuum Gaussian free field, essentially. So it's a Gaussian field or distribution when things go a bit rough, where the covariance is the Green's function of the biharmonic operator, with, I think if you put zero boundary conditions here, it's going to be Neumann boundary conditions. So you have the normal derivative that's set to 0, other than the Green's function being 0.
Okay.
And yeah, it can be a random distribution, so it doesn't necessarily have to be a nice field. Nice, I mean Hölder continuous, let's say.
Yeah. Okay, I see. Okay, well, thanks again, and let's thank again Alessandra. And then